Hello, welcome back. We are on lesson number 3 today. Last time we looked at sets, we looked at functions, and I hope you followed that lesson and understood everything. So today we are going to look at a new concept called quantifiers. So what is a quantifier? It's something that will quantify. It will give us an idea about the quantity. So in mathematics we have two types of quantifiers. The first one is called the universal quantifier. That is for all. So for all is the universal quantifier, and we write it in mathematics using this symbol. And for example, I can say for all x in R, x square is bigger than or equal to 0. So the quantifier gives a quantity to this statement, x square bigger than or equal to 0. So we have this statement x is a real number, x square bigger than or equal to 0. This says for all x in R. That gives me a quantity of the number of x's. So for every x in R, x square is bigger than or equal to 0. The second quantifier we have is called the existential quantifier, and that is for sum. So for sum, and then we write it using this symbol here, and here is an example. For some x in R, x is bigger than 0. So this is our statement, x is a real number, x is bigger than R, bigger than 0. So now my quantifier gives meaning to this statement by saying for some x in R. So these are the two types of quantifiers. For all is the universal quantifier. For some is the existential quantifier. So what does a quantifier do? A quantifier converts an open sentence to a statement, because now we can see whether this sentence is a statement, meaning whether it's true or false. So here are two more examples for you to look at. Here's an example. For all n, I'm using the universal quantifier. For all n in R, 2n is bigger than n square. Now, if I didn't have that, it will be an open sentence, so I don't know whether that's true or not. But if I say for all n, then I know this is a false statement, because if I try n equals 3. This is a false statement if I try n equals 3. Because n equals 3, I will have 8 on my left side, and this will be 9. So 8 is not bigger than 9, so this statement is false. And here we have a true statement, because it is now quantified. It says for some n, n 2n is bigger than n square. For some n, when I say for some n, I only need to produce 1 at least. If I can produce 1, then for some quantifier holds true. So here I can give say n equals 1. If I give n equals 1, then 2 to the 1, that's 2, is bigger than 1 square, which is 1. So 2 is bigger than 1. So I have an example here, n equals 1. So for some, it's true. When you say for all n, it must hold for every single n, but we know that it doesn't hold for n equals 3. So that statement is false. This statement is true. Therefore, these are statements, because we can determine whether they are true or false. So that's how we use quantifiers. In some instances, we can use what's called nested quantifiers. That means I will use two quantifiers. So what's called nested quantifiers? Nested quantifier means I use at least two quantifiers. Use at least two quantifiers. So for example, if I write you an statement like this, for all x, for some y, y is bigger than x and xy belongs to R. So here is a statement, and you need to learn how to read this. So for all x in real numbers and for some y in real numbers, y will be bigger than x. That means another way to read this is to say, okay, you give me any x for every x in the real numbers. So here are my real numbers. This is my real number line. I can take any x on the real numbers. For all x, for any x in the real numbers, I have a y. There exists a y. So for some, that means I need to produce at least one y which is bigger than this x. And I can easily do that if I choose my y to be bigger than x. So I will choose y equals x plus 1. So if I choose my y to be x plus 1, it's a number bigger than that x that you are choosing, then this statement is true, and we have what's called the nested quantifier. That means for all x, there exists a y which is bigger than that x. So you give me any x, it doesn't matter, whatever x you give me, I can always find a y that's bigger than that x. So that's what these nested quantifiers mean. So we are going to use these quantifiers. There are only two, for all or for some. So we will see how to use them again. We are going to look at functions again, a few more properties of functions. The first thing we want to look at is called surjective. So a function f is said to be surjective. Sometimes it's also called an onto function, if the range is the same as codomain. Now if you remember what we talked about in the last lesson, we talked about a function and it has three sets in connection: the domain set and the codomain set and the range set. So here is a diagram. So that's what a function does. It maps numbers from the domain into the codomain, so into the range. Range is a subset of the codomain. So all we need to do is to show that these two sets, the range and the codomain, are equal. So if we can say that, then it's called an onto function. So but already we know that range is always a subset of the codomain. So to prove that a function is surjective, we need to show that the codomain is a subset of the range, because then we'll have that the two sets are equal. If you have an example, here is a linear function fx equals 2x plus 1, and this is surjective because the domain of this function is R and codomain is always R. So we have domain R, codomain R, because we have a function from real numbers into real numbers, and for this particular function the range is also R. Since the range is also R, the codomain and range are equal, so we have a surjective function. So you can see the diagram and you will see that the range is equal to the codomain. Just sketch the range here, and the range here is the same as the codomain, so that's a surjective function. And we have also what's called as a second property, an injective function. So a function is said to be injective, that's the second property. We sometimes call it one-to-one. If f of x1 equals f of x2, then definitely x1 and x2 have to be the same, because if the fx1 is equal to fx2, that means for 1 to 1 there should be only one value. That means your x1 and x2 also have to be the same, so that's only one value. It's not two values. If you have these two equal, then x1 must be equal to x2. That's the property for injection. And that is for one value of y in the range, there is only one value of x in the domain. Now, by the definition of the function, we already know that for one value of x in the domain, there can only be one value in y. So now injective functions have the reverse property as well, that there is only one value, for one value in y, there can only be one value in x. So that's why it's called 1 to 1. So 1 of 1 maps to 1 of that, and 1 of that only maps to 1 of this. So such a function is called an injective function. So here's some examples. If you look at the linear function, 2x plus 1 is injective, as only one value maps to one value. So you can take any x, there will be only one y for that x, and if you take any y, there will be only one x for that. But if you look at the quadratic function, the square root function, that's not injective, as we can see that if I take a value in the range y equals 9, that's getting mapped into by two values of x, plus 3 or minus 3. So that's not injective because it's violating the one-to-one criteria. In a one-to-one criteria, only one value can go into one value. So this is not an injective function. A function that has both these properties, both surjective and injective, is called a bijection. It's just a terminology we use to call a function a bijection that's both one-to-one and onto. Such a function is called a bijection. Right, the next thing we are going to look at is limit of a function. This is a concept you are already familiar with from high school. So we'll quickly go through that. So let me look at an example here. Suppose we have the square root function fx equals x square, and we know that as x approaches 3, fx, the function approaches 9. So that's how we write the limit. So x is approaching 3, but you need to be sure that I'm only approaching. I will never ever achieve x equals 3. I will only approach, but not ever be equal to 3. I will get closer and closer and closer to 3, but will never become 3. So as I'm approaching 3, fx will approach 9. And we write that statement in using this limit notation, lim, like that. And you can see that as I'm approaching 3 from this, the graph comes down towards 9, and when I'm approaching 3 from this side, the graph increases to 9. For of course the limit to exist, we need both left and right hand limits. You know all these things. So we have the right hand side limit and the left hand side limit. If they both agree to a common